Okay, class. In our last lecture, we considered some of the different factors that go into determining the rate at which a coronavirus spreads. Remembering back to our early lectures about derivatives, we realized that calculating the derivative of this function allows us to determine how fast the rate of infection might change in response to changing conditions. However, we also realized that unlike most of the functions we'd worked with previously, this function was a function of 14 different variables, four of which we as a society have some control over. We thus can't take a simple derivative like we did in previous toolboxes. Instead, we need to learn how to take a partial derivative if we want to further investigate how our own actions could impact the rate of spread of the coronavirus. So let's go ahead and review the definition of the partial derivative and then learn how we actually compute partial derivatives. As a reminder, we only need the concept of the partial derivative if we're looking at a function of two or more variables. For instance, let's say we have a function that is a function of both x and y. In that case, we can define the partial derivatives of f of x comma y with respect to x and y in a similar way to the way in which we defined the normal derivative. We'll state that for all points at which the limits exist, the partial derivative of f with respect to x at the point x equals a and y equals b is defined as the partial derivative of f with respect to x at the point x equals a and y equals b is equal to the limit as h approaches 0 of f of a plus h comma b minus f of a comma b, all divided by h. The partial derivative of f with respect to x at the point a comma b could also be stated as the rate of change of f with respect to x at the point a comma b. Similarly, the partial derivative of f with respect to y at the point x equals a and y equals b is equal to the limit as h approaches 0 of f of a comma b plus h minus f of a comma b, all divided by h, and is the rate of change of f with respect to y at the point a comma b. If we allow a and b to vary, we can also compute the partial derivative functions df dx and df dy, which will vary across the range of x's and y's over which the function is defined. Now let's go back to this example in which you're hiking across some hills. X corresponds to distance in the east-west direction. Y corresponds to direction in the north-south direction. To distance in the north-south direction. And we have a function f that is a function of x and y, where f of x comma y is the elevation at the point x and y. As I mentioned last week, we could imagine that we were walking eastward. In that case, we would be moving slightly uphill while we walk to the east. Our rate of upward ascent with respect to our rate of horizontal travel is really the partial derivative of f with respect to x. The partial derivative is the incline in the eastward direction. We know that the slope or incline will vary based on where we are in this hill. It will vary while we walk around. So let's actually look at how it varies as we walk to the east. Remember, the partial derivative with respect to x is really just how much we gain in elevation divided by how far east we've walked. Or in other words, it's the slope of the line tangent to our curve that is traveling along the landscape. I'm now showing you, on the top plot on the right, the elevation as a function of eastward distance when we are at a y value of 5. We thus write this as f of x comma 5 because x is changing along our line through the landscape, but our north-south position is staying constant at 5. On the bottom, I've graphed the partial derivative of f with respect to x. This really equates to the incline in the eastward direction along our line through the landscape. You can think of that top plot as a cross-section through the landscape at y equals 5, and the bottom is just the slope of the tangent line for the curve on the top. So if we think of it like this, we're basically thinking of the partial derivative much the same way that we used to think of the regular derivative. And we can see how it varies as we travel along the side of this hill. We're pretty much always heading upwards, but sometimes we're hiking pretty steeply upwards, and hence the partial derivative is very positive. And other times we're hiking almost flat, and the partial derivative is closer to 0. But of course, we know that our eastward incline does not only depend on what x position we are at. It also depends on what y position we are at, because, like all landscapes, this one is complex with multiple hills and valleys. So what if we were at different y positions? Well, this time let's start further south and let's walk to the north. But while we're walking to the north, we're still going to pay attention to the eastward incline. Or in other words, we're going to walk north, but look to the east and measure the eastward incline. This means that we're still paying attention to the partial derivative of f with respect to x. We're just watching how the partial derivative with respect to x changes as we change our y position. So that graph on the top right is still showing the elevation as a function of x, but now it's not staying at just f of x comma 5. It started at f of x comma 3, then f of x comma 4, then f of x comma 5, then f of x comma 6, etc. As it changes, we are seeing different east-west cuts through the landscape. And since we are seeing different xy cuts, we see that the partial derivative on the bottom also changes. This should make sense to you. The slope of the incline, if you look east, depends on where you are in the landscape, what longitude and what latitude. This means that if we want to really plot the full two-dimensional partial derivative with respect to x, we're going to have to show it in 2 dimensions. So that's what I'm going to do here. The plot on the top right now shows our partial derivative of f with respect to x as a function of both x and y. Note that on this color scale, blue colors mean a negative partial differential of f with respect to x. That would mean that we would be going downhill if we walk to the east. On the other hand, a red color means a positive partial differential with respect to x, which means that we would be going uphill if we walk to the east from that point. Let's watch how this actually changes as we travel through the landscape. The red line on the left is showing you the eastward direction. So when the red line is pointing in an uphill direction, the partial derivative should be positive and will be going uphill. When the red line is pointing downhill, the partial derivative should be negative. So if we watch this for a moment, we see that right now it's pointing downhill, so we've got blue colors in our partial differential plot. Now we're moving to an area where heading eastward, we're traveling uphill slightly, so it's slight red. Now we're reaching a point where we're going to start going downhill a little bit, and so our partial derivative is blue for a second. Here now we're at a point where we're climbing steeply up the hill if we face eastward, and so we're at a really red color in the partial differential plot on the right. Now back to fairly neutral, then back to a bit of a slight incline, then heading back to a bit neutral again, and now we're actually getting to a point where we actually look downhill if we face in the eastward direction. Of course, we don't always think about the incline in the eastward direction. Sometimes we're more interested in the incline in the northward direction. In that case, we can go through the exact same approach. Now we can think of taking a slice through the hillside that is at a constant east-west value with x equals 5. And we can see how that cut through the landscape varies in elevation, as shown in the plot on the top right. If we walk along that line, of course, we're walking up over the hill and then back down to the back side of the hill. So our partial derivative with respect to y, which is shown on the bottom right graph and is also equal to the incline in the northward direction, will be positive while we're going up the hill, and then become negative when we start going down the back side of the hill. This is just showing us how the partial derivative of f with respect to y varies as we change our y value, but keep x constant. Of course, we can do the same thing measuring the northward incline or the partial derivative with respect to y while varying our x value, or in other words, traveling eastward. As we do this, we are moving our section through the landscape progressively further east, although our section itself is always a north-south cut through the landscape. We can see that the shape of our partial derivative doesn't really change that much, but the elevation does steadily get higher and the peaks and troughs of the partial derivative get steeper. Like with the partial derivative with respect to x, the partial derivative with respect to y clearly varies as a function of both x and y. The plot on the bottom right shows the partial derivative of f with respect to y, or in other words, the incline as you face northward, and we can see how the partial derivative varies as we travel through the landscape. When we're in sort of the middle of the north-south part, we have a very steep northward incline because we're really on the edge of that hill. Then as we head a bit further south, we get to a point where we're down in the valley, and now our partial derivative is actually pretty flat, or we're now a little bit negative. We're actually heading downhill if we go to the north. As we start to get out of that valley and come back up onto the hillside again, our partial derivative will start to be facing upwards again. And so now we're again heading into that red portion of the partial derivative graph on the bottom right. And of course, we can compare the partial derivative with respect to x in the top right to the partial derivative with respect to y in the bottom right. You should notice that the partial derivative with respect to y is often much steeper than the partial derivative with respect to x, with deep reds and dark blues common in the bottom right figure. This reflects the fact that the hills are generally steeper if we are traveling north-south than if we are traveling east-west. You also see that there are different spatial patterns to the partial derivative with respect to x and the partial derivative with respect to y because of the complex structure of the landscape. Okay, but how do we actually calculate those values? Well, let me show you the function that I wrote out to make those hills. I wrote out that f of x comma y equals the cosine of y plus 1/3 cosine of x plus 1/5 x plus 1 over 6 times the cosine of x times sine of x. This creates a landscape of rolling hills in 3 dimensions, although the fact that we have that 1 over 5 times x term in there means that over the long run it will gradually increase as we move to the east. Okay, that agrees with our elevation plot, as it certainly should, since I created that plot by inputting that equation into MATLAB and graphing it. So how do we compute the partial derivative from that equation? Well, let's remember our official definition of the partial derivative. The partial derivative of f with respect to x, evaluated at the point a comma b, is the limit as h approaches 0 of f of a plus h comma b minus f of a comma b divided by h, and the partial derivative of f with respect to y is the limit as h approaches 0 of f of a comma b plus h minus f of a comma b divided by h. Let's focus on the first equation for the partial derivative of f with respect to x for a moment. And let's compare that derivative to the normal definition of a derivative of a function of one variable. This is our old familiar definition of the derivative. The derivative of f of x with respect to x equals the limit as h approaches 0 of f of x plus h minus f of x divided by h. Okay, let's compare that equation to our partial derivative of f of x comma y with respect to x. First, let's note that the way that we've written our partial derivative so far, we're defining it at the point x equals a and y equals b. So let's do the same with our regular derivative. Now, if you look at that, it looks really similar. The only thing that is different is that in the partial derivative equation, we have f of a plus h comma b and f of a comma b. But remember, b is a constant. It's not b plus h in there or anything like that. We're just evaluating the derivative when y equals b. Okay, so let's write that out. F of x comma b equals cosine of b plus 1/3 cosine of x plus 1/5 x plus 1/6 cosine of x times sine of b. Now, let's remember that b in this equation is just some constant. Let's pretend that it is 0 for now. If b equals 0, we know that the cosine of 0 equals 1 and the sine of 0 equals 0, so we can just rewrite this equation as f of x comma 0 equals 1 plus 1/3 cosine x plus 1/5 x plus 1/6 cosine x times 0. Now, y isn't in that equation at all, and we know how to take the derivative of this function with respect to x. It's simply going to be equal to negative 1/3 sine x plus 1/5. All right, that's the partial derivative of f with respect to x for all x's if y equals 0. But of course, we could do the same thing for any other combination of x's and y's. So let's try that again. We'll rewrite our function for f of x comma y when y equals b. This time, instead of replacing b with 0, let's replace b with pi over 4. Let's go ahead and rewrite this so it's a bit easier to read. F of x comma pi over 4 equals cosine of pi over 4 plus 1/3 cosine of x plus 1/5 x plus 1/6 cosine of x times sine of pi over 4. Of course, we know that cosine of pi over 4 and sine of pi over 4 are both just constants. The cosine of pi over 4 is the square root of 2 divided by 2, which is basically 0.71, and the sine of pi over 4 is also the square root of 2 divided by 2. Okay, since those are just constants, we can take the derivative of this with respect to x pretty easily. Let's go through this piece by piece. Cosine of pi over 4 is simply a constant, so the derivative of a constant is 0. The derivative of cosine x is negative sine x, so the derivative of 1/3 cosine x equals negative 1/3 sine x. The derivative of 1/5 times x is 1/5. Next, we can remember that 1/6 times the sine of pi over 4 is just a constant, so we can multiply that constant by the derivative of the cosine of x, and the derivative of the cosine of x is negative sine of x. Okay, so far we've been doing this for specific different values of y, but we don't have to do that. We could figure out values for all possible y's if we want to. Let's just rewrite our function for f of x comma y, which equals cosine of y plus 1/3 cosine of x plus 1/5 x plus 1/6 cosine x times sine of y. Now let's remember that if what we're trying to do is compute the partial derivative with respect to x, what we're doing is looking at how the function changes with small changes in x, but with y staying constant. So we can treat y as a constant, and therefore the cosine of y and the sine of y can both be treated as constants with respect to x. If we know that we can treat them as constants, it's really easy to compute the partial derivative with respect to x, which is equal to 0 because the derivative of cosine of y with respect to x is 0, plus negative 1/3 sine x plus 1/5 plus negative 1/6 sine y times cosine x. Note that the last term there actually comes from the fact that we treat 1/6 times the sine of y as a constant, and then the derivative of cosine x is negative sine x. All right, that's actually not too hard. Next, let's do the same thing to compute the partial derivative with respect to y. Okay, let's again start by simply rewriting our equation, but this time let's remember that if we're trying to compute the partial derivative with respect to y, then we're varying y by a little bit, but we're keeping x constant. If we can treat x as a constant, then all the terms that just have x in them are constants. In that case, it's really easy to take the partial derivative with respect to y. The derivative of cosine of y equals negative sine of y. The derivative of a constant is 0, and the derivative of the next constant is also 0. The derivative of the constant 1/6 cosine x times sine of y will just be that constant times the cosine of y. So that's all pretty easy. If we want to compute the partial derivative with respect to x, we just pretend that y is a constant and take the derivative with respect to x. If we want to compute the partial derivative with respect to y, we just pretend that x is a constant and take the derivative with respect to y. All right, let's clean things up, and then let's see how this actually compares to the graphs we made earlier. Remember, our function on top is what we're graphing in the hills above. The partial derivative of f of x comma y with respect to x is the eastward incline of those hills, and it's what we're plotting in the top right graph. The partial derivative of f of x comma y with respect to y is the northward incline of the hills, and is what I've plotted on the bottom right. Take a look at those equations for a moment, and you'll see that those equations actually describe the colors that you're seeing in those graphs on the right. All right, let's switch gears now. Let's talk about how the temperature warms in the ocean around Antarctica in the spring. During the winter, the temperature is basically right at the freezing point of salt water, which is negative 1 or 2 degrees Celsius. The cold air temperatures lead to convective mixing, and the well-mixed ocean has a temperature profile that's constant with depth. However, Down in the regions that I study, the temperature now actually warms up fairly rapidly in the spring and summer months. Climate change is leading to much warmer air temperatures, and those warmer air temperatures will heat the surface ocean, and eventually that warm water will make its way down deeper into the ocean. We could write an equation for how the temperature changes at different depths if we know the initial temperature of the water, which I wrote as T naught in that equation, and also the temperature of the air, which I wrote as T air. Now, of course, the temperature will be a function of both depth and time, because it will constantly warm up, but the surface will be warmer than the deep ocean while the heat makes its way downwards. So let's plot this and see what it actually looks like. This graph shows temperature on the x-axis as a function of depth on the y-axis for any specific time point. And you see it's walking through time as we go from our initially cold and well-mixed water column, then start to warm it up from the top down. Okay, this shows us how the temperatures are changing as a function of time and depth when I assume that T air equals 5 and T naught equals -1. But what if we want to figure out how fast it is warming at different depths, or what the temperature gradient with depth actually is? These things are important. The rate of warming at any specific depth is equal to the partial derivative of f with respect to t, and it will determine how much thermal stress organisms living at that depth might feel. On the other hand, the vertical gradient of temperature, which is equal to the partial derivative of f with respect to z, will determine how stratified the ocean is, and the amount of stratification affects how well algae can stay in the well-lit surface area, and also whether or not nutrients get mixed from the deep ocean to the surface ocean. Alright, so let's talk about calculating those partial derivatives. Let's start with a partial derivative of f of z comma t with respect to z. This is going to be equal to 0 plus -6 times the derivative of 1 minus e to the -0.3 z over t. The 0, of course, comes from the derivative of a constant, and the -6 comes because we're multiplying the next part by -1 minus 5. Next, we can simplify this sum by splitting up the derivative of 1 minus e to the -0.3 z over t into the derivative of 1 minus the derivative of e to the -0.3 z over t. Next, we take the derivative of both of these. The derivative of 1 is, of course, equal to 0, and the derivative of -e to the -0.3 z over t is going to be equal to -1, which was the original constant in front of the exponential, times -0.3 over t, which is the constant in the exponent with z, times e to the -0.3 z over t. And this all simplifies to -1.8 divided by t times e to the -0.3 z over t. Alright, we've got the derivative. Now let's plot it at a couple different time points so we can see what it looks like. These graphs show f of z comma t as a function of depth in blue on the top two plots, and the partial derivative of f with respect to z in red in the bottom plots. The plots on the left are at a time of 5 days, and the plots on the right are at a time of 30 days. Note that at a time of 5 days, the ocean has really only just started warming up, so the surface is much warmer than the deep ocean, and the vertical gradient is much stronger, or in other words, the partial derivative with respect to z is much greater, particularly in that top layer of the ocean where it's warming rapidly. By 30 days after we've started warming the ocean, we see that the temperature gradient is much smoother, and the temperature in the deep ocean is closer to the temperature in the surface ocean. For this reason, the partial derivative of f with respect to z in the bottom right graph is much lower than the partial derivative of f with respect to z in the bottom left graph. This tells us that there will be more mixing 30 days after warming than there will be 5 days after warming started. Alright, next let's think about how the temperature will change with time at a specific depth. That requires that we now compute the partial derivative of f with respect to time. The calculation starts off similarly. The derivative of 5 with respect to t is 0, and then we have -6 times the derivative of 1 minus e to the -0.3 z over t. But this time we're calculating the derivative with respect to t. Again, we break it apart into negative 6 times the derivative of 1 with respect to t minus 6 times the derivative of negative e to the negative 0.3 z over t with respect to t. The derivative of negative 6 times 1 will be 0, so we just need to figure out the derivative of negative 0.3 z over t. Remember that this is just a function of a function, so we need to apply our chain rule that tells us that the derivative of negative e to the negative 0.3 z over t will be equal to the derivative of negative 0.3 z over t with respect to t times the derivative of e to the g, where g is the function negative 0.3 z over t. So this gives us negative 6 times negative 1 times 0.3 z times t to the negative 2 times e to the negative 0.3 z over 2. If you're not clear on what I just did in that step, please go back and review Toolbox 7.4 on the chain rule. Alright, at this point all we need to do is simplify our function, and we get 1.8z times t to the negative 2 times e to the negative 0.3 z over t. Now let's graph it like we did before. The top two plots show f of z comma t in blue as a function of time on the x-axis. The bottom two plots show the partial derivative of f with respect to t in red. This means that they are showing how the rate of change of the temperature varies with time. The plots on the left are for a depth of 5 meters. The plots on the right are for a depth of 75 meters. It should be pretty clear from these plots that the temperature warms up rapidly at 5 meters depth shortly after warming begins. In fact, it reaches a peak amount of warming of about 2 degrees Celsius per day. After that, the warming at 5 meters slows down because it becomes almost as warm as the air. At 75 meters, however, the rate of warming is never this fast. In fact, it is always much less than 1 degree Celsius per day and warms slowly and gradually throughout the spring and summer. All right. Let's go back to our study of infectious disease outbreaks. In Toolbox 8.1, we derived an equation for the number of people who get infected each day. F of n tot, tr p to p, s dist, ex, d public, tr con, v persist, c freak, s, q, da, d tot, gamma, p sus equals the infection rate for asymptomatic individuals times the total number of people infected times 1 minus the fraction that is showing symptoms plus the infection rate for symptomatic individuals times the total number infected times the fraction that is symptomatic. Okay, then we estimated that the infection rate for asymptomatic people equals tr p to p times 1 over 1 plus s dist squared times ex squared times d public plus tr con times v persist over 1 plus c free times v persist times ex squared times d public, and that the infection rate for symptomatic people equals s times tr p to p times 1 over 1 plus s dist squared times ex times 1 minus q ex times d public plus s times tr con times v persist over 1 plus c freak times v persist times ex times 1 minus q times ex times d public. Finally, we computed that the fraction of people showing symptoms was negative dA over d tot minus dA minus gamma dA minus 1 plus the square root of dA over d tot minus dA plus gamma dA plus 1 squared minus 4 dA over d tot minus dA all over negative 2 dA over d tot minus dA times p sus. Note that our equations were a function of 14 different variables, which are all shown here. Please note that in the 4 days that I've been working on this lecture, and since I finished the last one, we've learned more about the virus, so I've updated some of these values from the last toolbox. With that caveat, let's remind ourselves of what these parameters represent. N tot is the total number of people already infected. I'm estimating that the actual number infected is now 100,000 people. Next, we've got tr p to p, which is the transmission rate for person-to-person interactions, and I'm going to guess that it equals 5 times 10 to the negative 4 based on information we have showing how rapidly the virus has spread in different countries. Next, we have s dist, which is the social distancing that people keep between each other when they're in public. I'm going to start off by assuming this parameter a value of 0.1 feet, since most people, at least as recently as a week ago, were still getting very close to each other in public. Next, we've got the number of excursions or trips per day. This basically means every time you go into a different location that has multiple people. It could mean every time you walk into a store or into a classroom or go into a different building at work or the cafeteria. I'm going to assume that in their normal lives, most people go on something like 12 trips per day. After that, we've got d public, which is the density parameter. I'm going to assign a value of 1 for the density parameter for a normal city like Tallahassee. But remember, this will be higher for Miami and lower for Crawfordville. Up next is TR_con, which is the transmission rate for contact with surfaces. I'm going to guess that it is 10 to the negative 4. After that, we have V persist, which is the length of time that the virus can survive on a surface, and I'm going to estimate that that is equal to 1 day. Next is C freak, which is the frequency with which surfaces are cleaned. I'm going to estimate that C freak is typically equal to once per week, or 1 over 7 days. Then we have S, which is a factor calculating how much more infectious someone who is showing symptoms is relative to someone who is not showing symptoms. I'm going to estimate that this is equal to 10, because we know that symptomatic people will be coughing and sneezing and generally spreading the virus over a much wider area. Next, we've got Q, which is the proportion of sick people that are actually quarantined and don't go out at all. I'll estimate that Q is normally equal to about 0.5, because probably 50% of people with a common flu will completely stay home and not go out at all. After that is DA, or the duration of time that a person is asymptomatic, which is probably about 7 days, and then we've got D top, which is the total duration of the disease, which I'm estimating is equal to 3 weeks or 21 days, meaning that people are asymptomatic for 1 week and then symptomatic for 2 weeks. Next, we've got gamma, which is the exponential rate of increase of the disease, which currently seems to be about 0.3 per day. And finally, we've got P sus, which is the percentage of people who are susceptible to the disease, which I'm estimating at 70% or 0.7. Remember, all of these equations, our parameters, are just things that I'm estimating. Even the medical health researchers at CDC don't know the best numbers to put in here or the most accurate equations to use, so I certainly do not. But these estimates give us a starting point for using some of our mathematical tools to investigate the spread of the disease. Let's remember that the parameters that I've shown in red here are the ones that we, as a society, can directly change. The amount of distance you keep between yourself and other people, the number of excursions you take per day, the frequency with which we disinfect surfaces, and the proportion of sick people that we identify and quarantine. And if we want to determine which of those will have the greatest effect, we need to compute the partial derivatives with respect to each. So let's get to it. First, let's note that none of those red parameters are in the function for fsimp. So we'll be able to treat that as a constant that is equal to 0.1674. That will simplify things for us. Okay, let's start by taking the partial derivative with respect to social distance between people, or s_dist. The partial derivative of f with respect to s_dist means taking the partial derivative of f while all the others remain stationary. Since n_tot and fsimp are not functions of s_dist, we can treat them as constants, which means that our partial derivative of f with respect to s_dist will be equal to the partial derivative of I asymptomatic with respect to s_dist times n_tot times 1 minus fsimp plus the partial derivative of I symptomatic with respect to s_dist times n_tot times fsimp. So now we need to calculate the partial derivative of I asymptomatic with respect to s_dist. Note that s_dist is not in the second half of the I asymptomatic equation, so that makes it a constant with respect to s_dist, so it will go away when we take its derivative. TR p to p, ex squared, and d public are all constants with respect to s_dist, so we can pull them out in front, which means that we need to find TR p to p times ex squared times d public times the derivative of 1 plus s dist squared with respect to s dist. All right, as we try to compute that derivative, let's remember that 1 plus s dist squared equals 1 plus s dist to the negative 1. So what we really want to compute is the partial derivative of 1 plus s dist squared to the negative 1, which is equal to negative 1 times the part inside the parentheses raised to the negative 2 times the derivative of the part inside the parentheses, which is equal to 2 times s dist. And we can rearrange this to negative 2 times s dist divided by 1 plus s dist squared. Now let's plug this back into our equation for the partial derivative of I asymptomatic with respect to s dist. And we now find that the partial derivative of I symptomatic with respect to s dist equals tr p to p times ex squared times d public times negative 2 s dist divided by 1 plus s dist squared. All right, next let's look at the equation for I symptomatic. Again, we can just cross out the second half because s dist is not in the second half. Now you should notice that the rest of the equation is really very similar to the equation for I asymptomatic, except that we have a couple extra constants in there, specifically s and I minus q. So it should be really clear that the equation for the partial derivative of I asymptomatic with respect to s dist is equal to the partial derivative of I symptomatic, except that we need to multiply by s and replace ex squared with ex times 1 minus q times ex. We can now write an equation for the partial derivative of f with respect to s dist by plugging in these two equations. We find that the partial derivative of f with respect to s dist equals tr p to p times ex squared times d public times negative 2 s dist over 1 plus s dist squared times n tot times 1 minus f simp plus s times tr p to p times ex times 1 minus q ex times d public times negative 2 s dist over 1 plus s dist squared times n tot times f simp. We can now plug in any combinations of our 14 variables, whatever we think is most appropriate, and we can compute how fast the infection rate would decrease if we change the distance that people keep between each other. I plugged in the values that are my current best guesses, and with those values I get a partial derivative of negative 7,122. This means that with every extra foot of distance we keep between each other when we go out in public, we would reduce the amount of newly infected people by about 7,000 people per day. Now we could go through this exercise for every one of our 4 variables, but this toolbox is already running long, so I'm just going to tell you what they are. Okay, here are the equations for the partial derivative of f with respect to q, the partial derivative of f with respect to ex, and the partial derivative of f with respect to c freak. These equations are pretty ugly, but they still aren't that hard to plug into a calculator to estimate the number of infections that could be prevented by taking some of these actions. So let's see what we get if we plug in some of these equations. Okay, we find that increasing the number of people quarantined leads to a decrease of infections of over 14,000 per day. Decreasing our excursions by 1 per day leads to a decrease of 2,335 infections per day. Increasing our cleaning frequency decreases the infection rate by 1,841 per day, and increasing the distance between people decreases the infection rate by 7,122 per day. Okay, this suggests that our best steps are to try to do our best to identify and quarantine the sick people, while also increasing the distance we keep between us and other people while we go out in public. But remember, I'm not certain about the parameters we're using, so we might want to try other parameters. In particular, I assumed for these values that we were still behaving the same way that we used to, going right up to strangers, going from place to place 12 times per day, and that we only had 50% of sick people staying home. What if we'd gotten much better about these things? What if all of us were already adopting better practices, and we only went out in public once every other day on average, and everyone maintained a 6-foot barrier, and only 20% of sick people actually ventured out? What results would we get then? Well, in that case, we find that, first off, Our overall infection rate has gone way down, so we get less savings through additional action. But of course, this is great. We want the overall infection rate to go down. We now also see that under these modified scenarios, the most important actions that we can take are to increase our social distance even further and to minimize how often we go out into public. That's an important takeaway from this exercise, and something that we can actually apply in our daily lives as we try to decide the best ways to combat this outbreak. Now, keep in mind that these numbers are just my best guess. I'm obviously not an epidemiologist. The experts are still trying to figure out the specifics of this virus to determine what equations are best to use and what parameters should be chosen. Also, you probably won't listen to this toolbox for at least another week, and this disease is moving so rapidly that the data I'm showing you now may be out of date by the time you hear it. Nevertheless, I hope this shows how partial derivatives can actually be useful for real-world problems. Now, please go ahead and take the online quiz.